All right, today we're going to look at exponential and log models. So we're going to look at actually applying everything we've learned to word problems in this section. So all our problems, there's many different types of exponential and log equations that are used in everyday life. We're going to look at a few, mostly exponential half-life, exponential growth, decay, compound interest, and some Newton's law of cooling. So we're just going to look at a few and some examples. So our first one is radioactive decay. We call this, mostly we're going to use this as half-life. And so when we look at this, think about our interest formulas and how everything was always the ending and beginning amount. So here is our formula. We have our Q of T equals Q0. 1/2 is for the half-life, and T over H. T is still our time. H is our half-life. It would be given to you. So think about it just like we did in our interest ones. This Q of T right here would be our ending amount. And this Q of 0 would be your beginning amount of whatever it is that we're looking at, whether it's bacteria, bugs, or whatever it is we're going through. Then we have our exponential growth model. So our exponential growth is n of t equals n of 0 e to the rt. Again, r is our growth rate, t is our time, and just like before, this n of t is our ending amount, this n of 0 is going to be our beginning. That's the same way in all of our models. So along with exponential growth, we have exponential decay. You'll notice it looks just like our exponential growth model. The only difference is when it's decay, the exponent is negative. So if it's positive, it's growth. If it's negative, we're decaying. Then we have our exponential growth with a special one, which is doubling time. So it's kind of like our half time. We have our n of t equals n of o. And then because we're doubling, I have a 2 in here instead of the 1/2, and then t divided by d. D is our doubling time. Again, that would be given to you just like our half-life would be given to you up here. And then again, this n of t is still our ending amount. This is still our ending, and this is still our beginning. Okay, and our last formula that we are going to look at is Newton's law of cooling, where it is our T of T equals T of S plus D0 e to the negative KT. So in here, some things that you need to know. Our DO is the initial temperature difference between the object and its surroundings, so it's something you would have to find. And if its surroundings have a temperature of T of S, so that's our surrounding temperature of everything, then the temperature of the object at time t is modeled by this function. K is going to be a constant we'd have to find, and t is our time. So we're just going to do a few examples of using these equations. So our first one is under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in our colony. So when we're looking at this one, we're looking at our doubling formula. So here's our doubling formula, and we just need to fill in what we know. So we know that it doubles every 3 hours. So this 3 hours right here is going to be our D. And we know the initial amount is 1,000, so that's our n of 0. So we're just going to fill that in. So our answer would be n of t equals 1,000 times 2 to the t over 3. So that's our model. When we want to find how much is going to be in it after 15 hours, that simply means that we're plugging in 15 for our t everywhere. So n of 15, I plug in 15 for my t. This becomes a calculator problem. I highly suggest you plug it into your calculator. Make sure you can get the right answer. So you should get 32,000. And then our last one, after how many hours will the bacteria count reach 100,000? Sorry for my dogs barking. We're going to look at this. So in our formula here, we want to reach 100,000. So that means I'm going to let n of t be 100,000. So we'll have 100,000 equals 1,000 times 2 to the 10 over 3. Solve it using the methods that we learned in sections 4, 5. So the first thing we need to do right here is divide by 1,000 on both sides. So we're going to divide by 1,000. So that will give us 100 equals 2 to the t over 3. Rewrite it in log form, just like we learned before. Log base 2 of 100 equals t over 3. Sorry, Wiley, no. Then right here, to get our t by itself, we would need to multiply by 3. So 3 log base 2 of 100 equals t. So solve, this is just a calculator problem. Plug it into your calculator, and our t is approximately 19.93 hours. So there's example 1 for doubling time. Example 2, according to the U.S. Census Bureau, the world population from 95 to 2003 can be modeled by the exponential equation, and it gives it to us. T equals 5 represents 1995. P is in millions. So according to this model, when will the world population reach 7.1 billion? So here we just need to plug in to our equation, but you have to pay attention to your labels. So our P is in millions, and it gives us 7.1 billion, so we have to change that to millions. So if I change 7.1 billion to millions, it's 7,100. And then we just plug that in, and then we're going to use all the rules that we've learned to solve this. So the first thing we'll do is divide by 5,340. You can simplify that. I recommend simplifying it. I did not on here, but you can. Rewrite it in log form. So since it's an E, we have to use our E. So ln of 7,100 over 5,340 equals our 0.012922t. Again, then we would need to divide. Since this is a calculator, it's a word problem. You don't have to give me exact. You're just going to divide all that. So then in your calculator, you should get approximately 22.05. So this is how many years. But it asks us when. So when means I need to add 22 years to when we started, and we started in 1995. So if I add my years to that, I get 2012 is when that would have happened. Okay. Example 3 is Empire's population has grown exponentially from 326 people in 1952 to 12,044 people in 2012. So it actually grew exponentially since that time has already passed. We want to find part A right here, our annual growth rate. So to find our annual growth rate, we have to first start with our formula. So N of T equals NO e to the RT, and plug in what we know. So think about it. Our N of T is our ending. So our N of T is going to be our 12,044. Our beginning population was 326. And our time, how many years passed from 1952 to 2012? And that was 60, so we fill in what we know. And we need to solve this for R. So the first thing we're going to do is divide by 326. So I divided by 326, and I already simplified it when I wrote it down below right here. I simplified my fraction. Write it in log form. Since it's an E, we'll use our ln of 6,022 over 163 equals 60R. Again, you need to now divide by 60 to get R by itself. 0.0602. Whenever you're rounding your rate, always round to 4 decimal places. That way, when we change it into a percent, we still have some decimals in our percent. So we know that we have our R's 0.0602. So this would be our answer to part A. What is the annual growth rate? So that would be our answer here. Or you could say that it's 6.02%. Part B, if our growth rate remains the same, so if we keep that 0.0602, what year will the population reach 25,000? So you're going to come up here, you're going to have our 326E, we know our 0.0602 is for our R now, we don't know, we're going to figure out our time. It says in what year, so this Y is the same thing as our N of T. So we want to know when it will reach 25,000, so we're going to plug 25,000 in here, 25,000. Erase here so we have some room to work. So 25,000 equals 326 e to the 0.062t. Divide by 326. So I reduced it already. And I already wrote it in log form. So take some time. Make sure you understand where we went right there. Then we need to divide by our 0.0602. And to get our t, and you get approximately 72.09 years is how long it's going to take for the population to reach 25,000. And then again, it asks you in what year will that happen. So it's going to take 72 years. So we have to add 72 to our beginning time up here of 1952, and you would get the year 2024. So we are almost there on that one. All right, next example is going to be a half-life example. This is a real life. It actually is happening. So a nuclear accident occurred in reactor 4 at a plant near the town in the Ukraine. The explosion spread highly toxic radioactive chemicals, plutonium is what we're looking at, over hundreds of square miles, and the government evacuated the city and the surrounding area. So the evacuated area is still uninhabited today, and it'll be a very long time before habitation is possible. So we're going to use that scenario to kind of look at things. So in that scenario, the initial quantity of 10 pounds of plutonium was spread over the countryside in 1986. We know the half-life for plutonium is 24,360. So we want to find a model from that. So we know our initial quality and we know our half-life, so we can just plug that in. Here's our initial model. We know our Q is 0 is the 10 right here. Our half-life is the 24,360, so we're just going to plug that in, and there is our model. So we found our model. Okay, that's the first thing we're doing. Now I want to know how much plutonium is still present today. So to know how much plutonium is still present today, we need to know, well, how many years have passed since 1986 to 2021. So you need to figure out what your time is. So our time is going to be 35 years. So I'm just going to plug in 35 for my T. This becomes a calculator problem right here. So in our calculator, we can work that out. How much plutonium is still present, you would get 9.990 pounds approximately. It keeps on going, but we're going to stop right there. So that's how much is still left. And then our last part we want to look at on this is, when will the quantity of the plutonium be 8 pounds? So we look at that, when will it be 8 pounds? So we take our initial problem right here, or beginning one, and we want to know, when is it going to be 8? So now I need to solve for T. So again, first thing, rules that we've learned, divide by 10. So 4/5 equals 1/2 T to the 24,360. Rewrite it in log form. So log base 1/2 of 4/5 equals T over 24,360. So remember, to get T by itself, I need to multiply both sides by the 24,360. So here's a calculator problem. Plug all that in your calculator, you should get approximately 7,842 years. So it actually asks when, you would have to add that to 1986, so it's a lot of years when that will happen. So that is using our half-life formula. Our last example is a Newton's law of cooling. So we have a cup of coffee, has a temperature of 200 degrees Fahrenheit. We're going to place it in a room with 70 degrees. And after 10 minutes, the temperature of the coffee is 150. So the first thing we want to do is find a function that models the temperature. So our Newton law of cooling was this formula that I gave you at the very beginning. So things that we need to know. We know this 70 right here. This is our T of S. Okay, that's our room temperature. We have to find our D0. So D of 0 is the difference. If you look back at what I gave you at the first slide, D of 0 is our difference between the temperature at the beginning and our room temperature. So our D of 0 is going to be 200 minus 70, so it's going to be 130. So we're just going to plug those in. So I know that my T of S is 70. I know that my D of 0 is 130. Now we need to find our K, because we have to know what that constant is right here. So to find that, we're going to use this last sentence. We know after 10 minutes, it's 150 degrees. So this 150 can become our T of T, and our time is 10 minutes. So if I plug that in, we have everything but our K that we need to solve for. So now we'll use all of our rules for solving this equation that we have learned. The first thing we need to do is subtract the 70 from both sides. So subtract the 70, I get 80 equals 130 e to the negative 10k. Divide by 130. And then you can also simplify that. So I have 8 over 13 equals e to the negative 10k. Rewrite it in our log form. Since it's an e, we'll use natural log. So natural log of 8 over 13 equals negative 10k. We would then need to divide that by negative 10. All of this, it's a calculator at that point, and you get your k. We then have to plug that k back in up here to our original, because our first thing it said was find a function. So our actual function now is this. T of t equals 70 plus 130 e to the negative 0.04855t. That's our answer for A. Part B wants us to find the temperature of the coffee after 15 minutes. So we'll use that formula that we just found in Part A, and we know our time is 15 minutes, so I'm just going to plug in 15 for my time everywhere. And now this you can just plug straight into your calculator. So if we plug that into our calculator, you get approximately 133 degrees Fahrenheit. And the last thing it's asking for is, after how long will the coffee have cooled to 100 degrees? So we're going to take that beginning equation that we had from Part A, and we want our ending temperature to be 100, so we plug that in, and we need to solve for T. So again, now we are using all of our methods. So the first thing we're going to do, subtract the 70. So I get 30 equals 130e to the negative 0.04855t. Divide by 130 and simplify. So I simplified that to 3 over 13. Rewrite in our natural log form. So natural log of 3 over 13 equals negative 0.04855t. Again, we're solving for t, so now I need to divide everything by this and our log by that. Calculator problem again. So plug into your calculator. Make sure you're getting the calculator right. That's usually the part that we mess up the most. And we get approximately 30.2 minutes. It will have cooled to 130 degrees. So you have a worksheet that has at least one of all of these types of problems on it to work on, and I will answer questions when I get back. So have a great day, and let me know if you have questions or just bring them to class next time.